Good morning, everyone. So I just wanted to start with an announcement this morning. There is a STEM learning strategy session. This has nothing to do with me, but this is something that a STEM organization and learning center at OSU is putting together for some strategies to help you with your midterms, to talk about academic and wellness goals. If you're interested in this, there's a session tonight and tomorrow night, 5:30 to 6:45 in Ramsire Hall. That's the building kind of across the street from Wendy's on North Campus. So feel free to stop by. Apparently they're gonna have food too. So check this out. This is also on the lecture page if you want to get this link later. Just go to our lecture slide page and there's scroll to the bottom and you'll find this PDF page or this PowerPoint page. And also a reminder, I have office hours every day after lecture, so Mondays and Fridays from 9:10 until 10 a.m. And then today, Wednesdays, 9:10 to 11 a.m. And those are second floor of this building, room 2047, 2047 McPherson. If you forget that information, just go to Carmen, go to the contacts page. You'll see my office hours and location information there. So with that, let's do one other reminder for midterm 1 is next Tuesday in recitation. Next Monday, I will be here at 7:15. If you want to come early to bring some questions, feel free to arrive early. I'll take Q&A from the audience and go over whatever questions you guys have. And if there's no questions, I'll have a few review problems that I will go over. And I'll, of course, record and post this as usual, too, if you don't want to show up early so you can still benefit from watching that video later. But just a chance to see some review problems from me. And there's also a review Thursday night. It may actually conflict with the previous announcement, but there's a review session tomorrow night by one of our other instructors. I sent an announcement about that for the specific time and location for that, so check that information out. Okay, so let's look at another sig fig problem. I find these sig fig problems to be kind of interesting where, there's really just 3 rules. Addition, subtraction, we look at placeholders, and we round to the greater placeholder. When we multiply and divide, we just count sig figs, and we're counting the value with fewer sig figs and rounding appropriately. And then when we do multi-step problems, we just follow the order of operations. We just follow the addition, subtraction rule when we add or subtract in the order of operations, and likewise the multiplication division rule when we do that step. So let me give you guys a chance to think about this problem here. Take a minute or two. All right, so let's take a look here. So one thing that I would almost always do on a sig fig problem, you can still put the math into your calculator, not worry about the sig fig steps. Just do the order of operations. So if I put 0.00015 times 54.6 equals, and then do plus 1.002, we're trying to see how to round that value on our calculator screen. So if you get too worried about do I round once or twice, how do I deal with the rounding? The issue of the sig figs on the first number here, the 0.00819, is just to see where we're going to round the next result to. Like, I don't necessarily need to round this off. I'm going to round that value to 2 sig figs if I were to round it. but I could carry out the next step with it being 0.00819, and that's probably slightly better than actually rounding and doing the next step. Now, I've said this a few times. If you round here and then do the next step, you're going to get the same answer for test. This isn't going to be something for a test that's probably going to lead you to getting a different answer. This might be an issue in lab, where you're going from step A to step B to step C to step D, and if you round each time versus if you don't round each time, you're going to get a slightly different answer when you get to the very end. And so when it comes then to multiplying 2 sig figs times 3, so that's why I would round, if I were rounding just that first step, I would round it to 0.0082. I could keep it 0.00819 and just note that this placeholder is the last digit that's significant. And then 1.002, I just match up my placeholders accordingly, and I have to round to the value that's greater. So I'm going to round to the placeholder from that 2. That's the thousandths placeholder. So when I look at my calculator, I'm going to round to 1.011, or excuse me, 1.010. Now, I like to show units just because we're dealing with inexact quantities. The whole point here is that each one of these numbers is representing some type of a measurement that has an inexactness about it. And there's some uncertainty in the last digit. So the whole reason for sig figs, this isn't changing arithmetic. If these were just numbers, the result would be whatever our calculator said without worrying about rounding. But because these numbers here are trying to imply that there's some sort of measured quantity, I see units, or if I see a problem that just says assume, these are numbers to apply the sig fig rules, you're just assuming that those numbers represent measured quantities. There's a difference between this here being a number versus a measurement. Being a measurement means there's some inherent uncertainty in that last placeholder. If this was just a number, there's no uncertainty in whether that's 0.00015 or 15000 out to infinity. So the whole issue here is this inexact quantities, measured quantities. We have to look at that last placeholder as being inexact and having some inherent uncertainty to it. And that's what's causing us to round when we add and subtract or multiply and divide. So the result here would be answer C for 4 total sig figs. So whenever you see a multiplication step, the one thing that I see sometimes students do is you see a multiplication step and you see 2 sig figs and you might have thought the answer should have been B. But you have to think, well, that's just the multiplication step gets rounded to 2. We have to then apply the addition rule when we add and subtract. So just apply the simple rules in the order that you do the math operations and keep practicing. If this is something that you're getting stuck on, look at the daily quizzes. There's a bunch of examples there, and get to a point where you see these sig fig problems and you're like, this is something that hopefully you find to be a really easy problem when we get to next Tuesday at the real exam. Okay, so let's get into the last topic for chapter 2, which is dealing with nomenclature. And also through nomenclature, we'll see that we'll introduce some different categories of compounds that are important to kind of recognize some differences between the types of compounds in these categories and their behaviors. And some of the behaviors we'll be discussing as we continue into chapters 3 and 4 and beyond. So our first category, ionic compounds. These are, a really simple compound that we all know is sodium chloride's an ionic compound. This is a set of compounds where you have charges of cations and anions, and then you have the strong electrostatic force of attraction, so plus and minus are attracted together. So you have the electrostatic force of attraction just from the simple physics of how particles are attracted together. So you get a really strong force of attraction. This is why if you think of ionic compounds like sodium chloride, they have a really high melting point. Melting point of sodium chloride is like 800 degrees C because of that really strong attractive nature between the plus and minus charges. If we then look at a different category of compound, if I, and certainly you guys know some acids like HCl's hydrochloric acid. If you throw this into water, we call it hydrochloric acid. And so in water, what happens is HCl breaks apart into H plus and Cl minus ions. And then that's an important process that differentiates it from other compounds that tend not to release H plus ions. So most of our molecular compounds, now HCl is not ionic, even though I just wrote plus and minus. So even though it might be a little confusing right now that I wrote the plus and minus charges, HCl actually exists as a molecule where there's a bond between the two atoms. This covalent bond here makes this compound here a molecular compound. And it also contains non-metallic elements only. So a compound that only contains non-metals almost always going to be a molecular compound. There's a small exception with compounds of ammonium. We'll see those in chapter 4 later. So if you came up to me after class and said, well, what about ammonium chloride? I'd say, okay, we'll talk about that in chapter 4. So most compounds of nonmetals are going to be molecular compounds. So what you want to think about in this compound, HCl, do we have charged ions? We don't. We don't have H plus and Cl minus like we do Na plus and Cl minus in an ionic compound. What makes an acid is really its behavior in water. That's a topic for chapter 4. So what really makes acids special is a topic that we'll visit in chapter 4. But the idea for now will be that we will see a lot of ions we develop for naming ionic compounds. If you look at the anion and you have it paired up with H+, we're going to see that that's what an acid is. And we'll see a bunch of examples. This is just meant to introduce the idea and category of compounds as acids. So what you'll recognize acids as is a hydrogen with an anion that you kind of recognize from some nomenclature we'll go over for ionic compounds. And then later in chapter 4, we'll see that what makes acids special is they release that H+ ion when they dissolve into water. We'll also look at some simple hydrocarbons like alkanes. Methane's the simplest of these, so CH4. We'll look at C2H6 for ethane, C3H8 for propane, C4H10 for methane. So we'll go over systematically how do we know how many carbons versus hydrogens there are as we go from 1 to 2 to 3 to 4 carbons, et cetera. How do we systematically name these compounds? We'll get into that as we proceed. But I think you've probably seen these types of formulas before. You probably recognize, most people in the room probably knew methane was CH4. So just kind of recognizing that as our simplest alkane. An alkane is a saturated hydrocarbon, meaning we have as many hydrogens as possible on carbon. Can't have an infinite number. Carbon forms 4 bonds, so we get 4 for CH4, and we'll see why it's 6 for C2H6 when we get a little bit later into the notes. And then alcohols are just where you replace, the simple alcohols are where you replace a hydrogen with a hydroxyl group. So if we replace one of the hydrogens on methane with the hydroxyl group, then we get methanol. And that's our simple alcohol of methane. Probably the more commonly encountered one in college is ethanol. So ethanol C2H5 with the hydroxyl group. So just replacing one of the hydrogens with the hydroxyl group gives you the alcohol. And so ethanol would be C2H5 with the hydroxyl group. Don't drink methanol. Don't sit here and think that any compound that I ever review just because we know the name of it makes it safe. Don't make that mistake. A lot of times you may think, oh, I know how to name nitric acid. It must be safe to work with. No, it's not. So a lot of things that you will know and recognize by name doesn't necessarily imply any kind of safety. Or just because you can drink one alcohol, kind of, ethanol is actually toxic. It just has, some limits that we can drink before we die. If you drink too much ethanol, it will kill you too. But if you drink a little bit of methanol, it can kill you as well. So don't imply safety just from knowing nomenclature and recognizing compounds. And then lastly, we'll name some compounds that we call binary molecular compounds. Binary just means 2 elements, but these are some common compounds we just want to systematically know how to name, things like CO over CO2. But the funny thing is you already know how to name those, I'm sure. I'm sure you know CO is carbon monoxide, and then CO2 is carbon dioxide. And so that's actually, those 2 names fit into the systematic way that we name other compounds. And so if I were to say, NO, you probably now know that's nitrogen monoxide. NO2 would be nitrogen dioxide. And so you kind of can already pick up a lot of nomenclature if you just kind of say, oh, I actually already know kind of some of these systematic names just from the compounds being important enough that I've seen them before. And so we'll get into all these categories and kind of go over their systematic ways that we name them. And then hopefully when we get to test time, we'll see a compound. One of the first things we generally want to do is think, well, what category is it in? That will help us name it. And so if we start to think about how molecular compounds are almost the categories 2 to 4. So those are cases where we have non-metallic elements. The only case where we have metals involved are ionic compounds. Ionic compounds are going to form predominantly between metals and non-metals. And so if you see a metal paired up with something that's not a metal, probably going to be an ionic compound. Just so that when we start seeing formulas, categorize it, think of what the name would be according to that category. Okay, so as I mentioned, compounds that are ionic are comprised of cations and anions. And so this is just the schematic of sodium. If it were in its atomic form, it would have 11 electrons. It's the 11th element, so 11 electrons, 11 protons. But if it takes its one extra electron that it could lose to give it a noble gas configuration going to 10 electrons, and if it gives that electron to the chlorine atom to go from 17 protons, 17 electrons, so it can pick up and obtain that 18th electron, so it can go to its noble gas configuration, then you end up with two sort of happy ions, if you will. Now, there's an important sort of part of the process here. It's not necessarily energetically favorable for sodium to lose an electron. This is something that's really confusing to students, I think. I think we sometimes drive home the message that that noble gas configuration is so stable that's why sodium plus forms. That's not entirely why sodium plus forms. Sodium plus forms through a process that requires actually a lot of energy to be absorbed. But once it gives the electron to chlorine, some of that energy is given back. So some energy is returned because the electron's more stable, if you will, on chlorine. But then you get the plus minus attractive force. So that attractive force is what really drives that process of taking place. As we get into thermodynamics in chapter 5, and you see more in chapter 19 later, you'll get a sense that what really drives processes to take place is being high up on the hill, like a bicyclist, and somehow being able to get to the bottom of a hill where you end up being more stable. What makes sodium chloride more stable are all of these plus minuses, forces of attractions that you get between the plus and minus ions in that solid. So you get a whole network of plus minus attractive forces. That's really the ultimate driving force for why sodium chloride forms. We see that in more detail in chapter 8. So just introducing it here, that plus minus attractive force is really why something like sodium chloride forms and then sticks together once those atoms ionize. And so what we want to do here in chapter 2, though, is really just try to understand that for looking at a formula, can we determine the name of a compound? So really the point of chapter 2 is going to be formula to name, name to formula, and not so much the details of why these compounds exist. We can at least appreciate that there's some charged ions that will form, and only those charged ions form when those elements form ionic compounds. The alkali group all form +1. It would take way too much energy to take a +2. So to have sodium +2 is just crazy high energy. So we're not going to form a sodium +2 ion, only ever a sodium plus ion. If we then look at the group 2A elements, the alkaline group, they're only going to form +2 charged ions. They're not going to stop at the +1. They're going to go ahead and lose both 2 electrons, go to the noble gas configuration, and then they're going to get a +2 attractive force with whatever ion they form as a result. And so you could pair these ions up with each other. So imagine we pair sodium up with chloride, so we get NaCl, but we could pair sodium up with the oxide ion. The oxygen group forms ions with a 2- charge, and a compound should be charge neutral. So we form 2 sodiums. We'd have Na2O to balance out a +2 with a -2 for overall neutral. A compound, if we're going to ship it, like a compound can't have a net charge. I always say if you have a buildup of charge, you're going to have a static release of electricity, you're going to have a thunderstorm, something crazy is going to happen. So your compounds, if you imagine it's in a bottle, it has to have a neutral charge. And so if you ever think of something that has a charge, it has to be counterbalanced with the opposite charge somehow. If we took magnesium, 2+, we could pair that up with, of course, chloride. It just would take 2 of the chloride, so MgCl2 would be the formula for magnesium chloride. You might see me do this a lot. A lot of times if you see me doing this, it's just making sure that when I write a formula, I don't include the charges in the formula, but I might show them to do the math and think about how I do the math. And then I'm going to show the charge per ion above, and if I have to do the math times 2, I'm going to show that below. So just the schematic for how I like to think about charges. I have a +2 for the magnesiums. I have a minus chloride. I have to have 2 of them to equal a charge of 0. So I do my math below, my individual charges on top. Now the charges for magnesium, oxygen, I can get those from periodic table placement. So I'm just looking at where these ions are on the periodic table. Magnesium +2, calcium +2, etc. for the alkalines. Oxygen groups forms a -2. We don't see too many examples with selenide or tellurium. So you're not going to see too many examples of those elements, but we'll see oxygen and sulfide in most of our examples that involve the oxygen group. And then we'll see fluoride, chloride, bromide, iodide as key examples for the halogen group. Now, you do see H plus going plus and minus, and this all depends on what it pairs up with. And so if I said you had calcium 2 plus pairing up with hydrogen, then you would know that hydrogen has to be in the minus state. So with hydrogen as a minus, that would be calcium hydride. Just making sure you see that this is an A here for calcium. So calcium hydride, CaH2. And then if I wanted to pair, say, oxygen up with hydrogen, of course, that would be H2O. But now, with hydrogen, this really isn't ionic. It's really not H plus and O2 minus like MgCl2 is ionic. MgCl2 is ionic in that the compound would have a magnesium 2 plus ion, a chloride ion, and then no electrons, no shared electrons between. Water is molecular, and the difference here is just that we end up with these covalent bonds between the atoms. And so that's just a big distinction in properties. What that's going to do are ionic compounds. This is kind of like a chapter 12 concept, but I think we can appreciate it here. Ionic compounds, really strong forces of attraction, high melting points and boiling points. Molecular compounds, weaker bonding between the molecules, so we get lower melting points and boiling points comparatively. Okay, so what are some things that we need to know here for naming metals? So this is kind of a summary sheet that's just going to kind of go over some things that we should know. Our alkali cations, we should know that those are just plus ones. We get those from periodic table placement. So just from having a periodic table, we can tell that the lithium through cesium group form plus one charges. Since hydrogen's not really going to form an ionic compound, I don't include the H plus here. Anyways, our alkaline elements, those are always plus 2. And then it turns out aluminum, being where it is, only forms a plus 3. And I think I didn't point that out on the previous page, that aluminum is forming only the charge state of plus 3. You can see that from 13 electrons to go to 10 has to lose 3 electrons. If you notice, I don't include boron. That's just because boron is kind of weird. It doesn't really form ions in the way aluminum does. So we're not going to see examples with boron. And likewise, gallium, indium, those elements aren't going to do the same. So we tend not to see too many examples from the group that aluminum's in other than aluminum. And then ammonium is an ion that we'll see sometimes. I think we should probably appreciate that if we have 4 hydrogens connected to a nitrogen atom, that's what we call ammonium. You might know that NH3 is ammonia. I don't think you need to know ammonia's name, but you probably know it from previous examples. And so if you know ammonia, and then if you add an extra H plus to that, you get NH4 plus, that's ammonium. The protonated, and this probably won't come up, and some of these are things that we just kind of name. You may see them, you may see us talk about them in later chapters. But if you have an H plus ion that's dissolved in water, this is a chapter 4 concept of writing AQ, that just means dissolved in water, that a lot of times we write that as H3O plus. And H3O plus is just the concept or the idea of a dissolved H plus ion in water, and that takes the name hydronium. So you'll see us talking hydronium more when we get to the acid-base chapters, and probably more into 1220 as well. And then if we have transition metals, so what about the charges? If you go back to the previous slide and notice that the transition metals, I didn't show you any charges really for the transition metals, they can take on a variety of charge states. Like chromium can form with a plus 3 or a plus 6 commonly, iron a plus 2 or a plus 3, copper plus 1 or plus 2. And a lot of these metals can also, in other circumstances, form other charge states. So I don't expect that you memorize any kind of nomenclature system or any of those charges for those transition metals, other than I will use Roman numerals, and the common system for those types of ions is that we use a Roman numeral system, so that the copper 2 ion, the Roman numeral is telling you the charge. So copper 2 is copper 2 plus, copper 1 with a Roman numeral 1 would be copper with a plus charge. So the Roman numeral is telling you the charge of that transition metal. Manganese 5, that would be 5 plus. And there's, so for transition metals, we'll give you the element name followed by a Roman numeral. And so then let's do a quick example of, let's say I do a compound like CrCl3 and say, well, what's the name of this? Well, I don't know if I've quite gotten to the nomenclature for ionic compounds. We'll go metal name, or the cation name, followed by the anion name, like sodium chloride. Notice it wasn't sodium monochloride, it was just sodium chloride. If we go to CaCl2, calcium chloride. I don't have to call it calcium dichloride because I know calcium's a 2+, chloride's a minus. I can balance out the charges just from my knowledge of those charges. So I don't have to put the tri here. If I'm naming this compound, I'd call this chromium, and then 3, why 3? Well, it's a 3+ charge. And I can deduce it's a 3+ because chloride's a minus. I have 3 chlorides, so CrCl3 with 3 minus has to have a 3+ charged chromium. So I deduce the charge on chromium to be 3+, and then I put the charge on chromium as chromium 3, and then chloride. So not trichloride, I don't need the tri, because chromium 3 is telling me with chloride being a minus, I just have to know it's a minus, then it ends up being CrCl3. Yes?
How do you know if the metal is negative? Do they have
Well, yeah, good question. So metals only go positive. That's a great question. And so our metals are pretty much everything until you get to the metalloids, which are zigzagging through the sort of group 3 to group 8. So from boron across to neon, if you zigzag through the group, and I wouldn't worry about the specific cutoff, but you can kind of see the elements that separate from like aluminum, silicon, phosphorus, germanium, arsenic. Those are the elements that are getting into having properties of a metal and a non-metal. But if you go to the left, which is pretty much 2/3 of the periodic table, only ever going positive in charged state. So metals go positive, non-metals will go negative. And the only non-metal that, metals go positive, non-metals go negative, and then hydrogen sometimes will go positive. But that's more a later issue. Okay, so we'll see a bunch of examples of ionic compounds. I just wanted to get us thinking about how we're kind of putting the metal and the non-metal name together here for ionic compounds. And then I put a few compounds here that are probably not something you'll see on test, but you'll see them come up in other examples later that I think are worth noting here. Mercury 2 is just the ordinary mercury 2+. So that's just a very ordinary ion. So if you look at mercury 2, that's exactly what you would think. Mercury, it's below zinc, element 80. Mercury 2+, mercury 2, nothing abnormal there. But mercury 1 is actually kind of weird where it's 2 mercuries bonded together for an overall +2 charge. So mercury 1 is a weird ion that it's 2 mercuries bonded together for an overall 2+ charge. And so this is kind of like a molecular type connection. So imagine you have 2 mercuries connected by some type of metallic bond. And then where each side has a positive charge, this is what we're implying by saying Hg2, 2+. And the only reason I bring this up, chapter 4, we talk about mercury 1 salts. And they have a different property than mercury 2 salts. And if the first time you see the difference between mercury 1 versus mercury 2 is in chapter 4, you might find that a little bit more confusing. So we'll get into this more in chapter 4. So that's the mercury 1 ion. And then for zinc and a couple other transition metals, they only form commonly with 1 charge state. And there's like a table in the book, and there's a point in the notes where some of the instructors thought that you should just know zinc is always zinc 2+. Like we really don't call zinc 2 zinc 2+. You know, like it's only ever +2. So you'll see zinc ion as zinc 2+, probably not on exams. We probably would throw the 2 in there just so you're not confused early in the class. But zinc only forms with a +2, so you'll see us usually not putting the 2 on with zinc. So we'll just recognize zinc ion, zinc 2+. Same thing with silver's only +1. So if you see silver chloride, then you can know that that's silver plus, chloride minus. Even though silver's placement on the periodic table doesn't allow you to predict it's only a +1, it only forms with a +1. So if we understand that and sort of have that understood, then silver is silver 1. So silver chloride is just AgCl. And then same thing with lead's +2. So the only charge state that's common in compounds is lead 2+. So you'll see lead chloride as PbCl2, where we're not necessarily telling you it's lead 2. And again, probably not something to worry about for exams of us getting that nuanced, but you'll see these come up in later examples, and you may be like, why aren't we putting the Roman numeral there? It's because they only form those 1 charge states. So if we know that, then we tend to not put the Roman numerals on. But for the other transition metals, and really the point of our exam that we take next week will be to test the Roman numeral system. So I'm not trying to test these little nuances. So this is probably not something too much to worry about for the exam, but just later when we start naming things and using lingo, as we get through the class, you may see us not put the Roman numerals for zinc, silver, and lead, and it's just because we're understanding those charges. For the test, I would say just know to use the charge system. And like we have more slides to get into on naming ionic compounds. So, because I want to get to the cation and the anion and put them together for the ionic compound. So we still have to get through all the anions we need to learn how to name. And then putting it together is very simple: metal name, non-metal name. And so for the transition metals, it's really just recognizing name, the symbol to name. So like if I say iron, knowing it's Fe, so that little detail for the test is like not getting caught up on which element symbol we're talking about. So knowing to use the Roman numeral system, if I say what's iron 3 chloride, FeCl3, versus iron 2 chloride is FeCl2. Okay, so some simple ionic compounds. I don't know if I'll go through all of these. In fact, I wanted to try this thing out and see if this works on the fly. I knew this was going to be tricky. There's a way I can type the name, or I can handwrite the name that will translate it to text, and it's not working. I was doing this in my office, and I was like, I don't think this is going to work so well in this test. So there's some way, if I can figure this out, this will be great, because it will translate my crappy handwriting into text. So I will work on that maybe for the future. But for NaCl, just sodium chloride, and then MgCl2, magnesium chloride. And the big part here is just trying to drive home that we're not calling this dichloride. This is just magnesium chloride. I don't know if I'll write all these out, but calcium oxide for CaO. And now the anion nomenclature system, if you're saying, well, how do I know it's oxide? That's coming in a minute, but you've probably seen oxide ion and chloride ion. So we'll get to naming the anions in a minute. Sodium oxide, just showing you that we're not calling it disodium oxide. So we don't need to include dis, tris, tetras. You're gonna see that there's a category of compounds we do that with. We do that with carbon monoxide versus carbon dioxide. We'll do that with that binary group at the end, but we don't need to do that for our ionic compounds. Now, nitride, the IDE ending is just for a simple atomic ion. So nitrogen's nitrogen, so nitrogen would be N, nitride would be N3 minus. Why 3 minus? Nitrogen's 3 away from a noble gas count. So it goes to the 3 minus charge. Magnesium's a 2 plus. So how would we balance out the charge for a neutral compound here? How about we go Mg3 N2? If we double check our math, we get a 6 plus and a 6 minus. So we just have to get to neutral is why we go Mg3 N2. If I flip the 2's into 3's, if I did Mg2 N3, I'd have a 2 plus versus a 9 minus. They wouldn't balance out. So we just want to balance out our charge. If I did ammonium as NH4 plus, I could pair that up, and we'll see sulfate in a second. So we're definitely getting ahead of ourselves with sulfate, but you've probably seen sulfate before. If I told you SO4 2 minus was sulfate, you'd probably say, yeah, that seems somewhat familiar. We'll get into why that's sulfate in a minute. But if I had NH4 and if I knew sulfate were a 2 minus, we're going to do this. Now, why do I put the parentheses around the NH4? I don't need to put parentheses around a single atom because it's pretty clear if I say Na2 that I mean 2 sodiums. But if I put NH4 2 without parentheses, it'd be really confusing on what I meant 2 of. And so I use the parentheses whenever I have something molecular inside of it. So NH4 plus is what we call a molecular ion. Sulfate's another molecular ion. Yes?
So I had a question earlier, and you said that compounds have but I'm confused about how NH4 and SO4 have charges.
Yeah. So an ion will have a charge, but you couldn't have just a bottle of sulfate. It would be impossible to have a bottle just filled up with sulfate ion without there being something to counterbalance the charge. And so I could have a bottle of K2SO4, where I paired up with 2 potassium ions, but I couldn't just have the sulfate, or I couldn't just have ammonium. And when we talk about the nomenclature on the previous slide, we're just trying to learn how to name that cation part. And so none of those cations on the previous page would exist by themselves, but only paired up with a counterbalancing charge. And so I have 2 pluses and a 2 minus, so NH2SO4 is ammonium sulfate. Manganese versus magnesium is kind of the issue here. So manganese is the Mn, element 25. And a 4 would be a 4 plus. Oxide's a 2 minus. And so that would be MnO2 to balance out 4 plus, 4 minus. And then if I have the 5 version, the 5 plus versus the O2 minus. Now, I always think whenever they're not multiples, whenever the numbers just aren't easy to figure out, where it was pretty easy, I think, to figure out 2 versus the 4 plus, I cross multiply. And so if I cross multiply, I go with 2 and a 5, gives me a 10 plus and a 10 minus. So balancing out our plus and minus equally for Mn2O5. Now, I don't cross multiply here because I didn't need to. So I only cross multiply when I have like an even odd situation. Okay, so let's get into the ion side. And I did mention that sulfate was getting ahead of steam, and even like naming nitride, let's try to come up with some systematic ways for how we're naming the polyatomic ions, especially on the anion side. And so a polyatomic ion is just where you have more than one atom that share a charge. And so I would call NH4 plus polyatomic. I'd even include the Hg22 plus, that's polyatomic. So we have more than one atom sharing a charge. So a polyatomic ion, that's mercury 1. Sulfate with the 2 minus charge, that's a polyatomic ion. Now, if you get into the weeds here, you could, draw some structural formulas for like what this looks like, and I'll just do one for sulfate. And we could argue if you want over a couple Lewis structures, but this is a chapter 8 topic on what this thing kind of looks like here. I'm showing this here for you to get a sense that your ions like NH4 plus, SO4 2 minus, the ions, the atoms within that ion have these covalent bonds. So a molecular ion, we call it molecular because you have the molecular linkage of the atoms within the ion, where the overall ion shares a charge of 2 minus. And so the atoms within like SO4 2 minus or NH4 plus, those atoms are connected by covalent bonds, and then the overall collection of those atoms shares a charge. And so if you're pairing up charge here, maybe you put a sodium on either side to pair up the 2 minus with the plus, and then that gives you sodium sulfate. And this is a way of thinking, if we write Na2SO4, that the 2 sodiums aren't like connected together. The plus and plus, they want to be far away, they repel. So you put the sulfate minus plus plus, kind of breaking those ions up. Just giving you a sense that it's the plus minus attractive force. It's the attractive force between the plus and the minus that's keeping this compound together, why it exists in the first place. Now, why is sulfate a 2 minus charge, not a minus 1? That's not really a topic we get into in this chapter. What we're going to try to come up with is just what are some common formulas? What are their charges? What do we just have to memorize? We're going to have to memorize sulfate as SO4 2 minus. And we're not going to try to ask you why is it that formula. That's not a question for chapter 2. The question for chapter 2 is just what's the formula for sulfate? How many oxygens? 4. What's the charge 2 minus? What's its name when you pair it up with other cations? Putting that all together is the point of chapter 2. So name to formula, formula to name, understanding those formulas is our goal here. So now naming anions in terms of the other elements do this as well. So sometimes we call these oxygen anions or oxyanions or oxoanions, depending on the textbook that you use. Our textbook calls them oxyanions. So they're just anions of an element with a bunch of oxygens. And then what happens in nature is somebody just goes and finds, well, what count of oxygens and what charge is the most commonly seen for carbon? Turns out it's 3. So we call carbonate. So carbon is the central atom, 8 to imply oxygens. And then we just have to memorize for carbon, it's 3 oxygens with the 2 minus charge. And not much rhyme or reason, so we're just kind of memorizing the 3, memorizing the 2, go along with that name for carbon. So carbon 8, the 8 ending tells you it's the oxyanion, and then we just have to memorize for carbon, 3 versus 2 minus. Nitrogen, the common count that's most seen in nature is 3 oxygens with a minus charge. Now we don't ever see other charges. Like this is the only charge we see for nitrogen. The only difference you sometimes see is the oxygen count. And so sometimes you see the oxygen count drop by 1, but the charge stays the same. And so we'll end up naming this thing here in a moment, right on this, but we'll call that nitrite. So we have eights and ites. We'll even see we have hypoites and per eights. We'll see that range in a moment. But for now, let's just try to look at nitrogen. 3 oxygens with a minus charge is nitrate. Phosphorus is 4 oxygens with a 3 minus, that's phosphate. So we're just memorizing for phosphorus, 4 oxygens and a 3 minus charge is phosphate. Sulfur, we saw previously, 4 and 2 minus. Chlorate goes 3 oxygens with a minus. And so in terms of the periodic table, we're doing carbon, nitrogen, we're doing phosphorus, sulfur, chlorine. So these are kind of the elements where they are in the periodic table, and it just goes 3, 3, 4, 4, 3. Again, it's just pure memorization here. And carbonate's a 2 minus, minus, 3 minus, 2 minus, minus. And again, 3 minus to 2 minus to 1 minus. Maybe there's some rhyme or reason there for moving across the periodic table, going from 3 to 2 to 1. But the key is that you just have to kind of memorize that oxygen count and the charge to understand this nomenclature system. So there is just some memorization here. So if you're making flashcards, this is a slide to make flashcards from for sure. But it's just a couple of ions here. Has anybody ever heard the Nick the Camel ate a clam supper in Phoenix? Has anybody ever heard that series of words before? That's a silly moniker. I don't even care to write it out, but it's like the consonants or the oxygen counts and the vowels or the charge, and the first letter Nick was for nitrate. So Nick, 3 letters, three consonants for 3 oxygens and a -1. But I'll let you just hear it again. Nick the Camel ate a clam supper. If you're interested, you can Google it or whatever and go into more detail. I think it's just easier to flashcard this and memorize this than memorizing some silly moniker. Okay, so our naming anions. So this slide just puts it together for carbonate, nitrate, phosphate, sulfate, chlorate, and understanding those names and those formulas. And then we can also, as I mentioned earlier, change the oxygen count, but I'm not changing the charge off of what the ion originated with. So chlorate's a minus with 3 oxygens. So chlorite has 2 oxygens, but still that same minus charge. And then hypochlorite, probably one of the most used ions in everyday life, in terms of cleaning at least, in bleach. The hypochlorite is where we lose another oxygen, just go down to 1 oxygen. And so that's the hypochlorite ion. Now it turns out that sulfate, carbonate, phosphate, and nitrate don't lose that second oxygen. So this is pretty uncommon. Like only chlorate loses the second oxygen commonly enough that we name it. And we could name like hyponitrite as NO-, but it tends not to form so commonly, so we probably won't call that hyponitrite too often, but we could. It would fit the nomenclature system. It's just not as commonly seen as, say, the hypochlorite ion. And then what happens if you add an oxygen? If you go to ClO4-, again, you keep the charge the same, you're just changing the oxygen count. We call that perchlorate. You just have the per out in front, and we keep the ATE ending, so that's perchlorate. Now, there's one other ion that this actually is common in that we may not think about this all the time, but oxide we mentioned is O2-, and I know we've seen examples of the O2 2- ion in our everyday life. Do you know the name of this? We added an oxygen, was oxide, so this is actually peroxide. So peroxide, I will put this on my list of things that you probably don't need to know for exams, but it's worth knowing, that the per, you're just getting this by adding an O to the formula and keeping the charge the same. And so you probably know hydrogen peroxide. Don't drink hydrogen peroxide. I wonder if that's a demo we can do. There's an interesting demo. If you take hydrogen peroxide onto the enzyme in liver, you take like I think actual chicken liver and put it in a flask, and it just like foams up super quickly. So if you drink hydrogen peroxide, you're probably gonna puke. So don't drink that. There's that joke. I went to a guy at the bar, ordered an H2O. I ordered an H2O2 and I died, from drinking hydrogen peroxide. So again, just because you know the formula Doesn't mean you can drink it, but H2O2 is hydrogen peroxide with that peroxide ion underlying part of its like nomenclature on how we would name that. Okay, so that's the peroxide ion, perchlorate ion. So just kind of putting this together here, we have carbonate, nitrate, phosphate, sulfate. We can name nitrite, phosphite, sulfite very easily. We're just dropping an O off the base formulas that we've memorized. So sulfite, SO3, but still a 2 minus, PO3, but a 3 minus for phosphite. So these names here, I don't think we have to flashcard these necessarily because we're kind of learning a system. If you learn the system, you don't have to flashcard those extra 3 ions over here. If you learn the system for perchlorate, chlorite, hypochlorite, you're not necessarily flashcarding those names as pure memorization. You're more like learning the system. Add an O, it's per, take an O away, it's an ite, etc. So try to learn the system, I would say, instead of necessarily the ion nomenclature. And so then the O2 minus, add an O, that becomes peroxide. And so a few examples here, calcium nitrate. So calcium's still a 2 plus, nitrate, we just have to know it's a minus with 3 oxygens, so calcium nitrate, 2 nitrate ions. So just CaNO32. And then what's the name of this formula here? Ca3PO42. So I know calcium's a 2 plus. I know phosphate's a 3 minus. That's a 6 plus, 6 minus. So my pairing of charges makes sense. So I haven't made a mistake with my charges. And so that looks like calcium phosphate. I'm sorry, so carbonate. Yeah. I'm sorry, I'm just not understanding your question. So okay. So CO3 2 minus. Like occasionally we might name CO2 2 minus as carbonite. I don't know. Ask me after class. I'm so sorry. Yes. There's a few other ions that come up in some like examples that we treat as commonly named things like ammonium we treated in the cation case, hydroxides, the OH minus group. So that's the hydroxide ion. So calcium hydroxide would be calcium 2 plus, so CaOH2. Acetate's common. Acetate's interesting in that sometimes you'll see it written 2 different ways. The more formula descriptive way of writing it's CH3COO minus. This will make a little bit more sense once we're kind of picturing that the reason why that is because it literally has a CH3 group and then it has a carbon group that looks like this. And then that could pair up with like an H plus or pair up with other metals. So this is kind of what acetate looks like once we understand structural. So that's a structural representation. But a lot of times, especially in chapter 2, we'll write it C2H3O2 minus just so that we can recognize it as an anion a little bit easier as one of our anions. So we call that acetate. And so if you always think metal, non-metal, then it makes more sense to write K C2H3O2. If we write CH3COO minus and put K onto it, it might be a little bit hard, but the way we would write that would be like this. And we tend not to write that. I mean, like, it's not really common that you would ever see it written that way. But if we write it the second way, we're probably writing the formula with the K after. But you're so used to seeing the metal first that we tend to write it KC2H3O2. And you'll see when it's in acid form, we could write it either way. But we'll talk about that when we get to the acid nomenclature later. And then often not tested, but probably worth knowing, is that peroxide. And you can even have something called a superoxide, which is 2 oxygens with a minus charge. And so K plus with the O2 minus group is potassium superoxide. And these are only forming with certain alkali metals under some peculiar conditions. And so it's a really reactive compound. It's not something commonly you're going to run into, but probably not worth Probably not going to be on the test or anything, but you'll see examples of this later. You'll see in chapter 4, we go over some things about peroxides versus superoxides. So whenever you see TiO2, I want us to not get too confused about peroxides or superoxides, because these things here only form with like the first group and maybe the second group elements. They're not going to form with transition metals. So TiO2, I'm looking at this as the ordinary oxide ion. Oxide's a -2 from the periodic table, like chloride's a -1. So I get a -4, so that's titanium plus 4 oxide. And so putting this together for the anions, hydride, H- just from the periodic table placement. So just adding a minus for anion, for hydrogens, hydride. For the halides, chloride, fluoride, chloride, bromide, iodide, just from periodic table placement, we know those are all minuses from being in the same group together. Oxide, sulfide are primary examples of the oxygen group of anions. We see in a lot of examples with the O2- sulfide ion. Nitride, phosphide, 3- ions based on periodic table placement. So things in red are things that I'm just understanding based on where the periodic table is telling me information to get the actual charges. So I'm just looking at nitrogen 3 away, nitrogen 3-, nitride ion. And so the IDE ending is just that simple. So if I see the IDE ending for an anion, it's telling me it's a simple monoatomic ion, just single atom with the charge I can get from the periodic table. And then hydroxide is just a commonly named ion for the hydroxide ion, acetate, 2 different ways of writing it, and then carbonate, and then the other oxyanions that we had mentioned. And so hopefully we're picking up the systematic way of naming things like nitrite, phosphite, chlorite, hypochlorite, perchlorate, etc. Okay, so let's get into acids. So acids, once you see the anions, it's really easy to recognize an acid. And then hopefully when we sort of appreciate that they're molecular compounds, they have a different set of properties, that's why we kind of name them differently than ionic compounds, even though you will still be thinking of charge involved in these compounds. They just don't have those charges in the formulas we're going to write for them. And so if I have a simple ion like chloride, that would be HCl. So HCl is just hydrogen chloride. I put it into water, it ionizes. So in the formula, it's not ionized. That's why we call this a molecular compound, not an ionic compound. And so that's why we're not giving this some kind of weird ionic compound nomenclature system. We're giving it an acid nomenclature system. So we call this hydrochloric acid. So HCl, hydrochloric acid. If you then said, well, I could have chlorine with 3 oxygens, that's chlorate. If I put an H+ onto that ion and make HClO3, that's also a molecular compound, that's also an acid. An acid is where I can see an H in front of the formula, then an anion I know how to name. I'm looking at this at chlorate in acid form. I would call HClO3 as a formula, I'd call this chloric acid. So the nomenclature system for 8 ending ions, if the anion just ends in 8, I go to just changing it to ic acid in acid form. So ides, chloride goes to hydro element name ic acid. So hydrochloric acid for Cl-, Br- hydrobromic acid. But in the case of ClO3-, that would be chloric acid. If I go to HClO4, I just look at ClO4- as perchlorate, so HClO4 would be perchloric acid. And so acids are nice in the nomenclature system because the name tells us it's an acid. The name is blah, 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 acid. And so when you then get to later in the class, we're going to ask, well, what are a bunch of acids we know how to name or recognize? It's all these acids we learned how to name here in chapter 2. Now, if we have an ite ending anion like chlorite, we go to OUS, chlorous acid. So HClO2 is chlorous acid. So we add the ITE ending. If we have an ITE ending anion, it goes to OUS acid. Now, if you can appreciate, what we need to be able to do is we need to be able to name chloride, chlorate, chlorite, perchlorate, hypochlorite, and then all their acids they can form as different names. So if you have 2 different formulas for 2 different compounds, they should have 2 different names, so they don't have the same name. And so here we can name things like hydroiodic acid. Hydroiodic means we have the simple iodide ion in acid form, that's HI. Phosphoric acid, H3PO4. So it takes 3 H ions to neutralize the charge in phosphate ion. So phosphate's a 3-, so I need 3 hydrogens for phosphate ion. Nitrous acid, OUS, means we had to come from nitrite, which is HNO2. So I go HNO2. Hydrofluoric, sulfuric, sulfurous acid for those acids here. So I'm just looking at sulfate, sulfuric acid, sulfite for SO3, sulfurous acid. HF, hydrofluoric acid. This is one that's really worth pointing out. We'll end here for today, that hydrofluoric acid really drives home the message that just because you know the name doesn't imply safety. Hydrofluoric acid is one of the most nasty compounds to work with. It could kill you just by getting a tiny bit on your skin. So if you ever come across hydrofluoric acid, treat it with extreme caution. So very dangerous compound to work with. So just know, just because you know the name doesn't mean it's safe. All right, guys, that'll do it for today. We'll see you on Friday.